Geometry. So the title of this course to this point, we've been kind of just reviewing ideas from previous algebra courses and a little bit of geometry. Last time we talked about how we had our definition for sine, cosine, and tangent was defined on acute angles in a right triangle. Our goal here in chapter 2 is to take this rather specific limited definition and expand this Oh, thank you.
You're welcome.
So what we want to do here over the course of this chapter is take this definition of sine, cosine, and tangent, where we're looking at acute angles inside of a right triangle. And what's up? Oh, I'm not. Thank you. And extend that definition so that it is applicable for any angles and not even tied necessarily to a triangle at all. I realized I started working in the wrong spot here. You're famous for a second. There you are. Put that in the right spot. There we go. All right, but before we can get there, we have to lay a little bit of foundation as we start building this out. So over the course of this chapter, we're going to look at like 2 other definitions for sine, cosine, tangent that aren't linked to triangles at all, but that'll come next class. Today, we're just going to start by talking about how to measure an angle. So, one way to measure an angle is the familiar degrees method that we've been talking about all through geometry, and probably even a little bit before that. You talk about that probably in your pre-algebra algebra course. You probably do small amounts of geometry ideas there. And the second way that we'll talk about here today is the radian. And there's actually a third way called a gradient, but we're in a high school math class and you wouldn't need to talk about that here. So this one, the radians one, is the one that we're probably unfamiliar with. You may have talked about this briefly in your geometry course, but probably not. Let's start by defining what we mean by a radian. We say that a central angle has the measure of 1 radian if it intercepts an arc with the same length as the radius. Woof! Mr. Kulik, that's a lot of words. I'm not really sure what that means. If the definition doesn't mean anything to me, it's not very useful. Let's explain kind of what this means, because there's a lot of vocabulary in here. from geometry, and it's been a minute since any of us have been in a geometry classroom. So I'm going to just kind of do this with a picture. So here's a picture of a circle. That circle, we have a center. The center of that circle is the point A. We call something a central angle if the vertex of the angle is at the center of a circle. So like CAB in this case would be a central angle. Everybody feel good with that? When we say intercepts, well, that means that the central angle has to intersect the circle in some way. We see that both arms of our angle intercept the circle. And then it's talking about an arc. An arc is just part of the perimeter of a circle. In this case, our arc would be the arc CB that we'd be concerned with. That would be the intercepted arc, the arc between the arms of our angle. And then we remember what a radius is, right? So what we would say here is that if the radius AC is equal to the measure of the arc CB, and remember when we name an arc, we put like a little arc on the top of it for its hat, then the measure of angle CAB is 1 radian. Does everybody kind of see the picture now? So that's what the words are meaning. It's saying like, okay, if this thing and this thing are the same length, then that angle measure was 1 radian. So we now have 2 different ways that we can measure an angle. We can measure it with degrees, or we can measure it with radians. If I have 2 different ways to measure something, what are we going to need? If you have feet and you have centimeters, with 2 different ways to measure something, what do you need if you have 2 different ways of measuring something? A way to convert in between them, exactly, right? So I need to be able to say, okay, something is this many radians. Well, what's that mean in degrees? Or if something is this many degrees, how many radians is that, right? It's a natural thing that you want. You want a way to convert between one unit to the other unit. Let's build out what that conversion factor is going to look like. Sound good? So what I'm going to do is I'm going to take a circle. Oops. That looks like this. In this circle, our central angle is the angle CAB. What's the measure of angle CAB in this picture? 180 degrees, right? It's labeled in the picture, but how else would I know it's 180 degrees? It's a straight line or it's half the circle. Either one of those is fine. So our radius in this picture would be either AC or AB, right? Would you agree with that? And our intercepted arc would be the arc BC. Feel okay there? the measure of the arc BC should be what? Well, I know you measured arcs in geometry with degrees. We're talking about the arc length, though, the distance that it would take to walk from, one point to the other point along the arc. Isn't that half a circle? Should be half the perimeter of the circle, right? Or the circumference of the circle. And the circumference of a circle is 2 pi r. So that means that arc length is pi r. Okay. So, remember our piece before, that if the radius is equal to the arc length, then our angle is 1 radian. Everybody's okay with that? So here our radius is r. And what we want is to use this information that we've accumulated to figure out the radian measure for this angle CAB. Everybody's okay with that idea? Okay. So again, above we saw that if the radius length was equal to the arc length, then the angle measure is 1 radian, right? So here, our radius, or our arc length, is pi times the radius, right? What would the radian measure for CAB have to be? Has to be pi times, it's pi times as big, right? If they're both r, it would be 1 radians, right? If the arc length and the radius were both r, CAB would be 1 radian, correct? Everybody agree with that? How many 1r segments can we make on that arc length? If we divide it up, how many of those should we have in total? Pi of them, because that arc length is pi r, right? So the measure of CAB should be pi radians and since what was the measure of CAB in degrees? 180. We get that 180 degrees is equivalent to pi radians. And I guess that goes back and forth, right? Then pi radians is 180 degrees also. That's our conversion factor. That's like saying, 1 inch is 2.54 centimeters, or, like a yard is 3 feet, or a mile is 5,280 feet, or whatever, right? That's just our conversion factor. Everybody's okay with that? The 180 degrees is pi radians. So if I have an angle in degrees, actually I'm going to write it this way. And I want to convert that to an angle in radians. I would multiply by 180 degrees over pi radians. Or if I want to go from radians to degrees, I'd multiply by pi, or 180 degrees over pi radians. So those of you that are like in a chemistry class or recently, like that kind of conversion structure should look pretty familiar, right? Where you're just kind of like doing dimensional analysis and converting units. You do that a lot in chemistry. I don't know how much you do it in your other sciences, but at this stage, probably many of us have had a chemistry course. But that's the takeaway, right? This picture is really kind of the one that we end up thinking about. So that's just like the Greek letter theta. So that's the variable we typically use in a trigonometry course to represent the angle or an angle measure. So I put a subscript d on it to say an angle in degrees, and I put the subscript r on it to mean an angle in radians. Everybody's okay with that? Let's do a couple of examples here to just kind of make sure we're comfortable with what we've just done. So part A says to convert 90 degrees to radians. So I start with 90 degrees. And what do I need to multiply this by so that my answer is in radians? Well, we're doing like this path, right? Starting with degrees, ending in radians. Everybody agree? So pi radians over 180 degrees, right? Now, the convention when doing this is if we can leave our radian measure in terms of pi, we would like to do so. So what I'm going to do is I'm going to look at 90 divided by 180. Is there a common factor between, or a common divisor between 90 and 180? 90, right? 90 divided by 90 is 1. 180 divided by 90 is 2. So we're left with 1 times pi, or pi over 2. We okay on that? That's our answer. Very quick, right? No big deal. Now keep in mind, ooh, that one snuck up on me. We could also represent this as a decimal, right? So like 1.57. Why do you suppose we prefer the one in terms of pi as opposed to the decimal? What's up? Makes more sense. Okay. What else?
I'm just saying how you got it.
What's the difference between pi over 2 and 1.57?
Fraction.
Okay, what else? Is 1.57 the entire number?
No.
No, what did I do? I rounded it, right? Did I do any rounding for pi over 2?
No.
No, man. Why do we prefer pi over 2? No rounding, right? It's more precise. Is there ever a way, if I have a pi in there, that I'm going to get a decimal that comes out exactly? No. Because pi is irrational, right? So if you divide an irrational by irrational, it still comes out irrational. You'll still get an infinite, non-repeating, non-terminating decimal. So that's the reason why we tend to prefer an answer in terms of pi. Everybody feel okay? All right, let's go again. So let's say we have 152 degrees. And again, we want to multiply it by something so that we get an answer in radians. What are we going to multiply by?
Multiply by pi radius over 180.
Yeah, pi radians over 180. Or you could just say pi over 180 is fine. The radians can be implied. So again, we'd like to write this answer in terms of pi if possible. So let's look at 152 divided by 180. Do you guys see a common divisor between those two numbers? Well, 152 is definitely not divisible by...
That was 150.
That's okay. Are you sure? What are you sure about? 2, right? Because they're both even. So let's do that. What do you notice? Or is that as simple as we can go? They're both even, so we certainly can divide them again, right? So let's do that. 38. How about now? I think that's probably as good as we can go, right? So that's going to be 38 pi over 45. Or if you wanted to, you could type this into the calculator if it seemed more appropriate to have a decimal. Or if you were asked to round your answer to like 2 decimal places, we just type that into the calculator. And you say about 265. Everybody feel good on that? So the next one says we want to convert 2 pi over 5 radians. So multiply that by something so we can end in degrees. What do I need to multiply 2 pi over 5 radians by to convert it to degrees? 180 over pi. Yeah, so like the radians and radians cancel, so we're left with just pi's. I'm going to notice that between the 5 and the 180, those go in evenly, right? How many times does 5 go into 180?
13.
More than 13. How about 18? No, that's not right. How about 36? And then I notice also that the pi's can cancel, right? What are we left with then? 2 times 36. Now, could you have just typed that all into your calculator also? Sure. But just good review, just basic arithmetic review on how to like shortcut through multiplying fractions and stuff. But yeah, you could have typed that all into your calculator and just pressed enter, sure. Why couldn't we do that back here? Because of the pi. But you know what we could do, if we did 152 and then we dropped the pi and just wrote divide by 180 and then press the math button and choose the fraction command and press enter, that'll give us the reduced fraction. And we can just write the pi next to it. You guys see that? You've used the calculator to reduce fractions before? Okay, just double checking. And obviously there's no decimal equivalent to 72 degrees. 72 degrees is the decimal already, right? We never write that in terms of pi. Okay. So here we have 1.6 radians, and we want to convert that to a degree measure. What do we need to multiply 1.6 radians by? 180 over pi. Again, radians and radians cancel, but nothing else really cancels, right? So it's just calculator time at this point. Can't do it can't do it in my head. So I get 9167. And I'll change that to squigglies to show that I rounded. Certainly. So far, so good. Pretty easy, right? NBD. Okay. So let's now talk about the circumference of a circle. We should remember that the circumference of a circle is 2 pi r, right? Do you remember your arc length formula from geometry? That length was the measure of the central angle in degrees over 360 times 2 pi r. Everybody okay with that? Now notice that we can reduce this, right? The 2 and the 360 can reduce down. And then if we rearrange this, this would be like my angle measure in degrees times pi over 180 times r. What is that going to give me? If I take an angle measure in degrees and I multiply it by pi over 180. If I take an angle measure in degrees and I multiply it by pi over 180, what's that going to give me? Our angle measure in radians. That is simple right there. So you're telling me if my angle is in radians and I want to find the arc length, I just multiply that angle measure by the radius, and I'm done. Ooh. Yeah. So let's formalize that. We'll call that a definition. And just as a reminder, our degree version that we built from was that guy there. Let's do a couple of examples practicing using these formulas. All right. Example A says solve for S, that's our arc length. If the radius is 4 or 1.4 meters and the angle measure is 0.98 radians. Since we're in radians, I want the radian version. So my radius is 1.4. My angle measure in radians is 0.98. I multiply those together and I get 1.372. Now, this should have a unit on it, right? Because it's an arc length. What unit should be attached to this? Not radians, not degrees. It's a length.
Meters.
Should be meters. Whatever the unit that we use to measure the radius should be the same unit as our arc length. Let's look at example B. So in B, we know we're asked to solve for S if the radius is 3.8 inches and the central angle is 40 degrees. Notice there it's in degrees. So I'm going to use the other version of my formula. And now we just fill the stuff in, right? So pi, the radius is 3.8. The angle is 40 degrees over 180. When I type that through in my calculator, I get about 265.3. And what unit should this be in?
Degrees.
Inches. It's the same as the radius. So again, degrees and radians measure angle size, but like feet, inches, meters, things like that measure lengths, right? C says solve for R if S is 18 centimeters and theta is 2.13 radians. So again, I'm given a radian measure, so I'm going to use the radian formula. But this time we're asked to solve for R. So we're told 18 is S, and theta is 2.13. So R is going to be 18 divided by 2.13. when I type that through in my calculator, I get about 8451. And the unit here should be centimeters, yes. So it's, again, the radius and arc length should be in the same unit. I divided both sides by 2.13. I just wrote it so that the R was on the left, so it just looks more natural. Is that, you're good? Okay. Okay. One more example, and then we're done with this section. We'll start the next one after that. Okay, here it says, find the perimeter of a sector with a central angle of 1.7 radians, cut from a circle with a radius of 5 centimeters. What do I do with this? What's the word in here that's the problem? I would say sector. What the heck is a sector? Anybody remember what a sector is from geometry? No? It's a slice from a round pizza. So it's a pizza slice. Like that's our sector. You know, like just a slice out of a pizza, right? Everybody's cool? So if I wanted to write in the values here, here's my central angle. That's a radius. That's a radius. And that would be arc length. Everybody's cool? So if I want the perimeter of that sector, the perimeter is just the distance around. So in this case, that would be R plus S. Now, the radius we know, that's just 5. But S we need to find, right? Now, since our central angle is in radians, I'm just going to use the radian angle or arc length formula. So my perimeter then should be 5 plus 5 plus 8.5. And the unit here should be centimeters. Everybody's cool with this? Again, pretty easy, right? Once we understood what a sector was. Okay. Hi, Ms. Tardecki.
Hi, do you Will Lanham?
Yes.
Can I ask you a real quick question, Mr.
Yeah, you can take him for a minute.
10 seconds of his time.
I think he can spare 10 seconds.
I can scan. Real good. Thank you. I want to change it. Yeah. Thank you. Thanks for your time.
Did you really?
Yeah. I wasn't.
All right. Last one here. So this says a car has 18-inch diameter tires on it. If the car is traveling 15 miles per hour, how many revolutions per second are the tires making? So we need to go from miles per hour to revolutions per second. That's our unit conversion that we're being asked to do. Everybody square with that? So we're going to start with 15 miles in 1 hour. And somehow we got to end up in revolutions per second. Everybody's square on that. Now going from hours to seconds, that's pretty easy, right? We should know how to do that. I know that I have 1 hour is 60 minutes. And then 1 minute is 60 seconds. So when I multiply these fractions, the hours cancels with the hours, the minutes cancels with the minutes, and I'm left with just miles per second. Everybody's okay there? How am I going to convert miles to revolutions? That's the trick. How are we going to do that? Any guesses here? I'll give you a hint. We need this piece of information. Okay, let me ask you a new question then. How far is 1 revolution of a wheel? What? Not 18 inches.
Oh.
How much distance, though, is 1 rotation? Or 1 revolution of the wheel? It's gonna, 1 revolution is 1 circumference, right? You spin that wheel 1 time and you should go the distance around the wheel, right? That's how far that wheel will have rolled along the ground. Everybody's okay with that idea? Okay. So we need to go then from miles to revolutions via that circumference. So that's going to be 2 pi, and then what's the r in this case? Close. Nine, because we're given not the radius, but the diameter. Oh, Mr. Kulik. Everybody's okay with what I've done there? So in order to apply this ratio, I need my length unit to be in inches, correct? Right now it's in miles, so I just have to convert miles to inches and I'll be ready to apply that. How far is 1 mile? I don't know how many inches it is, but I know it's 5,280 feet. And then I know 1 foot is 12 inches. And then I know I've ran out of space here, so I'll just erase that for a minute. And then I know that 18 pi inches is 1 revolution. And then I'll be in, oh boy, revolutions per second. So miles cancels with miles, feet with feet, inches with inches. And we're left then with revolutions per second. Everybody feel okay there? Okay, let's type this into our calculator then. My suggestion to you is to use that fraction command that I've shown you guys a bunch of times. So I'm going to alpha y equals and pick that first option. In the numerator, I have 15. And then times 1, so I'm not going to bother writing that because it doesn't do anything. Times 1, not going to write that. Times 5,280 times 12, I'll type that one. Times 1, I don't care. Over 1 doesn't matter. Times 60 times 60 times 1 doesn't matter. 1 doesn't matter. And then 18 pi. So 60 times 60 times 18 pi. And I get about 467 revolutions per second. Oops. It should be back in red, huh? Hey, I already stole you. What do you guys think? That one's maybe a little tricky, but the key idea is that 1 revolution is 1 circumference. That's the key to doing any kind of, like this thing is going, is rolling this fast, and how many like revolutions per whatever is this, that's the trick. All right. Section 2.2. So here we're going to be talking about trigonometric functions of acute angles. This is basically the same thing that we reviewed from geometry, with one little addition. So we have some right triangle with acute angle theta. So I know that like sine of theta is opposite over hypotenuse, and like cosine of theta is adjacent over hypotenuse, and tangent of theta is opposite over adjacent, right? Like that's just SOHCAHTOA. Everybody agree? Now, have you ever noticed that, like, hey, Mr. Kulik, there's like 3 other ratios that I could write here. Like, why isn't hypotenuse over opposite something? Or like adjacent over opposite? Why aren't those things? Right? I can make that ratio. Why didn't we make that into a trig function? Guess what? We did! You just didn't hear about it yet. So let's write down what those are then. I know I'm excited too. Okay. You gotta go somewhere, right? All right. So these 3 new symbols here. We have cosecant, that's abbreviated CSC. We have secant, that's abbreviated SEC. And we have cotangent, that's abbreviated COT. Now, Mr. Kulik, does that mean I need to memorize like another like SOHCAHTOA thing? I'd say no. This is the way that I would remember this. I would just remember that sine and cosecant pair together because they are reciprocals, right? So if I remember that just cosecant goes with sine, I know sine is opposite over hypotenuse, so cosecant is the reciprocal, hypotenuse over opposite. Secant goes with cosine. So since cosine is adjacent over hypotenuse, secant should be hypotenuse over adjacent. Cotangent pairs with tangent. Since tangent is opposite over adjacent, cotangent is adjacent over opposite. So here's the tricky part, is keeping straight tangent, cotangent. It's easy to remember those two are like the reciprocal pairs, right? How do I remember that secant goes with cosine and sine goes with cosecant? That seems like that's hard. And I just remember that no cos go together. So cosine doesn't go with cosecant. So it has to go with secant. And then then secant is just the reciprocal of cosine. So it's hypotenuse over adjacent. So I'm trying not to have to memorize new things. I just want to like take something I already know and be like, oh, if I just think about it that way, it's just something I already know. I just have to remember like which one pairs with which one, which to me seems easier than memorizing like a new acronym. You know what I'm saying? Okay. All right. So that's the only new idea here is these 3 new trig ratios. So all of my example problems from here on out are going to be similar to things that we did last time when we reviewed right triangle trigonometry. So suppose we're asked to find the exact value for all 6 trig ratios for the theta in the right triangle given below. Okay. All right. So sine I know is what? Opposite over hypotenuse. What's the opposite in this case? What's the opposite in this case? 5. Okay. And what's the hypotenuse? Yeah, we don't have it yet, but we can find it using the Pythagorean theorem. So 2 squared plus 5 squared is equal to x squared. So 2 squared is 4, 5 squared is 25. We add them together, we get 29, and then square root both sides. What's the one thing we have to remember when we set up our Pythagorean theorem? The hypotenuse has to be the piece by itself, right? Okay. So we have 5 over square root of 29. Does that look good to you guys? I wouldn't leave my answer that way. What's wrong with it? Yeah, you have a square root in the denominator. How do I get rid of that? Yeah, when you say both sides, you mean the top and bottom. Yep. So 5 times the square root of 29 is just 5 square root of 29. What's square root of 29 times square root of 29? Just regular old 29. Great. Now cosecant should be easy now. What's cosecant going to be?
The opposite.
You mean the reciprocal. So what do I write? Square root 29 over 5. Keep in mind that when we did that, we used the one that before we messed around with it, because I don't have to worry about rationalizing the denominator. If I use the one that I already rationalized, well, then I have to rationalize the denominator again, then I'm going to have reducing to do, and it's going to be like this whole thing that is not important. Just use the one in the beginning, right? Okay, cosine is adjacent over hypotenuse. Adjacent is, and then hypotenuse is still square root 29. Oh no! We got to rationalize the denominator there again, but no big deal. So what do we end up with? Yeah, excellent. 2 root 29 over 29. And then secant should be square root 29 over 2. Tangent is opposite over adjacent. Well, I don't have to do anything with that. That's perfect just the way it is. So cotangent is 2 over 5. Beautiful. No big deal, right? We have these 3 new ratios, but so what? Anything different than the things we've done so far that we reviewed last time? No, man, it's like the same stuff. Okay, cool. Coolsville, Daddy-O. Does this get harder, Mr. Kulik? Eh, not really. Let's do another example of a slightly different kind of problem. So here it says, let theta be an acute angle of a right triangle if sine theta is 1/3. What are the values of the 5 other trig ratios? What am I going to start by doing? I'm going to start by drawing myself a picture. So there's theta. If sine theta is 1/3, I know the opposite side is 1, and the hypotenuse is 3. So to find the missing side there, I can do the Pythagorean theorem. But here I have to be a little bit careful. So 1 squared is 1, 3 squared is 9. When I subtract 1 from both sides, I get 8. So x is the square root of 8. Can I reduce that radical? You betcha, right? 8 is square root 4 times square root 2. And the square root of 4 is just regular 2. Everybody feel good? And guess what? From here, exactly the same as the previous ones, right? Now, what's cosecant going to be? 3 over 1 or just 3? Just 3 sounds good to me also. If you wrote 3 over 1, is it okay? Sure, but why do that, right? Just don't do that. It's fine, but like, come on, we're better than that. Cosine should be? Who can tell me what cosine should be? The whole thing. No, just do the whole thing. Numbers.
It'd be 1 over 3.
That's sine. 2 root 2 over 3. Yup, that happens.
Oh my God.
And secant should be, you can come in and sit down if you'd like. Secant should be what? Great. Is that the final answer though? No. What do we need to do? Yep. Multiply the top and bottom by root 2. So the top becomes just 3 root 2. And what's the bottom become? 2 times 2 or 4. Yes. Wonderful. All right. And then tangent would be? But the numbers?
1 over 2 times square root.
Great. Is that okay?
No.
No. What do we need to do?
Multiply by square root.
Good. So 1 times root 2 is root 2. And the bottom is? 4.
Oh, yeah, that was so silly.
And what should cotangent be then?
It's 2 times square root 2.
2 root 2 over 1, or we'll just write it as just 2 root 2. What do you guys think? No big deal, right? Same stuff that we've been doing. We just have these 3 other trig ratios to deal with, but like they're not a big deal because they're just the reciprocal of the ones we've already been using. So that's not a problem. Okay, let's look at this example here. Find sine 30 without a calculator. What makes this one hard? Without a calculator. How in the heck am I supposed to do this?
She saw without a calculator, she lost her mind. She was like,
This is too easy.
Let's start by drawing our picture. So I have the triangle. I'm going to label this as 30 degrees. What's the other angle have to be?
it's 6.
So 60.
Yeah.
Yep. So what kind of triangle is this?
3069.
30, 60, 90. Oh, that was a thing. Remember, that is a thing from geometry, right?
Yeah.
So the ratios of side lengths in a 30, 60, 90 triangle, the short side is x. The middle side is x root 3. The long side is 2x. So if I take that and I do sine of 30 is opposite over hypotenuse. The x is reduced down and we're left with just 1/2. Done. What was the other special right triangle that we saw in geometry? Do you remember?
30, 60,
40.
45, 45, 90. Guess what we're going to say about these guys? You should have those memorized for the test, but what would make these a good candidate for if I'm telling you to memorize them? Putting them on your half sheet. Yeah, because like you're going to use them a lot in this class. You should memorize them, but like, I don't trust myself to memorize it. I'm going to try to memorize it, but I'm putting on my half sheet also because, like, why take the risk, right? So far, so good. Everybody happy? Speed's okay. We're not going too fast or nothing. You guys keeping up? Okay. So this one says find sine 17 or find secant 78. What do you notice about this problem that's missing as composed to the other problem? The without a calculator part. So can I use my calculator to do this? Heck yeah, I can. All right. Before I punch this into my calculator, what I need to make sure of? Yeah, I got to check my mode to make sure I'm in degree mode. I switch back and forth all the time because I teach all these different classes. So I'm going to check back to degree mode. Sine of 17, well, that's easy. There's a sine button right on my calculator. So boom, there's my sine of 17. How do I do secant of 78, though? How do I do that? Do I have a secant button on my calculator? I do not, right? I just see sine, cosine, tangent. But what do I remember about the relationship between secant and cosine? They're reciprocals. So if I want to do secant of 78, I can just do 1 over cosine 78. And there we go. Secant is the reciprocal of cosine. So I'll just do 1 over cosine 78. Answer. What do you think? NBD? Not a big deal, right? Same stuff we've done. You just have these 3 new trig functions that can pop in. But like, whatever, Mr. Kulik, it's just like 3 other things to write down. I'm doing the same stuff I did. I just have 3 new things to include. Whoop-de-doo! I can handle this. This is where we're stopping today, guys. That was 2 sections. I think at this point, you guys should be able to do up to 42 from the problem set. Oh no! Seems like a lot of problems. Here's the good part, though. Like, I think the first 12 are literally like just converting from degrees to radians. There's like 10-second problems. You know, like, you know, there's a set of problems that are just like, you know, finding the arc length or finding the, you know, the radius from the arc length or the central angle from the arc length, like not a problem, like quickie, like, you know, 15-second problems or something. Like, there's some trickier stuff in here, but for the most part, I think it's pretty okay. You know, like use the calculator to do like sine 22. Woo! That's a tough one, you know. So I would say half of this problem set is pretty like just I'm typing one line into my calculator and pressing enter and then writing down a number and just boom, 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 bing, 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 boom, boom. But this is where I'm stopping today, guys. Next time we're going to start constructing this new definition for sine, cosine, and tangent. So we'll go in phases. But we have some building to do. So the next 2 lectures are kind of like conceptual theoretical because we're building out this new definition, showing how we get to that. But the good news is that the end result is easy to use. So we got that going for us. But I'm going to stop talking now.